Hi everyone, and welcome for this presentation on WebAssembly. So I hope you're good today. I'm very sad for not being able to attend SuriCon this year, and I just hope I'll be able to see you next year. So today we're going to talk about WebAssembly. And first of all, I'm going to give a few words about myself. So my name is Pierre Chifflier. I work for ANSI, especially in a detection research lab. And my main hobbies are parsers and introducing more raw stuff in Suricata. It's now many years I've been a contributor. It gave me some kind of, first commit in 2010. So we are going to talk about WebAssembly, which is also called WASM. So I'm going to use both words for describe the WebAssembly environment and virtual machine. We're going to describe a bit the security features and what is interesting for us. And then I'm going to describe what can go wrong at some point and what is interesting for detection tools like Suricata. And what are the main challenges associated with these interesting features? Because WebAssembly is going to change many things, as we'll see. So first of all, I'm going to give you an insight about what WebAssembly is. So looking at the name, you could think that WebAssembly is 50% web and 50% assembly, which is kind of true. But in some way, it's also wrong because WebAssembly is, as a common joke, we often say that WebAssembly is neither web nor assembly. It really is something more like the definition of a bytecode. So it's binary format, which is meant to be executed in a virtual machine. And this virtual machine is going to be isolated. That means it's going to be separated from your browser, for example, because it's meant to be executed in a browser. And then this isolation is here for your security. So it's here to solve problems. These kind of problems are the problems brought by JavaScript, Flash, and other kind of technologies we're currently using. So WebAssembly was developed by W3C community group and is defined mostly for the web environment. But as we'll see, you can find WebAssembly outside the web. You can find it in cloud-based environments, Kubernetes, and so on. So here our main focus will be on the web and web browsers, but it's not only the only use case you can find for WebAssembly. So what is it really? Well, it's kind of similar to what you can do with when you are trying to compile an application for your usual environment, for example, Linux, Windows, and so on. So an application is usually compiled from a source code and transformed by the compiler into a binary. And this binary is going to be executed on your host to execute the application. WebAssembly is really bringing the same technologies for the web. So the source code will be compiled to some binary, and this binary will be distributed to the browser, and the browser will be able to execute it on whatever your underlying system is. So it's going to be fast because it's binary and not interpreted code like JavaScript. It's going to be portable, and it's going to be supported in many different browsers and environments. And again, it's not only for browsers, it's also used in so-called serverless applications, IoT, blockchains with smart contracts, and so on. So one question you might ask is, can I use it yet? And the answer is yes. In fact, there's a huge change. You are already using it without even knowing it, because all browsers, except maybe Internet Explorer, but who uses it except for downloading Chrome these days? So all current browsers already support WebAssembly. including smartphones. And that is so since several years. So today, since more than 94% of the browsers already supported, there's a huge chance you already executed it. What kind of application can we find in WebAssembly? Well, here I listed a few applications, maybe the biggest one, because it's not mostly the most representative applications for WebAssembly, but you can find things that would be huge and previously impossible to compile for a browser. So you can find game engines, and the complete Unreal game engine supports WebAssembly, for example, and the famous Lichess platform uses it for its client application. You can find huge applications like AutoCAD for 3D design. It's also embedded in blockchains and so on. And you can find projects which are more things to show what WebAssembly is capable of, like Vim, and maybe someday LibreOffice, because everything goes to LibreOffice one day. So there is a project trying to port LibreOffice to WebAssembly, which may increase the performances and the capabilities of the editor from a user point of view. And also, as we'll see, malwares are already using it, because why not? So what does it look like? Well, as I said, it's binary, so it's not really interesting unless you're willing to read binary, which is a very interesting hobby. So WebAssembly is a very compact format. Usually the binary can be small, unless, as we'll see, a ton of code is embedded. It's a very simple module structure, so it's fairly trivial to disassemble, and it's characterized by a magic number, so we can recognize it very easily. The WebAssembly specification gives the definition from not only a binary code, but also a text format, which is called WebAssembly text, or WAT. So on the left, you can see a simple, very simple Rust program computing the Fibonacci sequence number. It takes 32 bits integer and returns same integer. It is compiled by WebAssembly, by the Rust compiler, to the right side code. Well, if you're not very used to that, it may look very complicated, but in fact, it really is simple. It's a very simple assembly language, which looks like the assembly language you can find on an x86 machine, even simpler, in fact. So, well, this is usually the text you can look at right now is usually the text we will be manipulating when disassembling WebAssembly. What other things are important? WebAssembly is designed to be simple, because simplicity is one important thing for security. And especially in the specifications, there is no support for multi-threading, SIMD, exception, garbage collection, and so on. And in particular, also a very important feature is that WebAssembly does not access what I call the outside world, meaning from the virtual machine, you cannot access the host machine executing the WebAssembly VM. For example, a WebAssembly application cannot access the HTML structure to modify it directly. This is a key point because it's important both for security and also to be able to control what the application is doing. You might wonder at this point, well, is it really working? Is it that fast? And the answer is yes, it is. For example, you can look at a screenshot from a complete x86 machine emulator written in WebAssembly. So it emulates a full virtual machine, and it's running Windows 98 and trying to connect to the Suricata IO website. And you can see the old warning from Windows 98 telling you are about to access a secure connection, which is something that we would like to avoid right now. We would like to be warned when we are not accessing a secure connection. So the virtual machine is in itself pretty much working correctly and emulating a full architecture, full x86 architecture in the browser without any problem. So on the performance side, I'd say, okay, the challenge is done. It's working, it's fast, it's okay. So what about security now? By design, WebAssembly is designed to run untrusted code, because what you are loading in the browser is going to be really untrusted. So the key points here, again, I'm not going to be able to go into details. I give you pointers at the end of the presentation for more complete descriptions. So the memory is self-contained. The WebAssembly virtual machine is not able to manipulate pointers, but only index. That is important because if there are no pointers, this removes a lot of errors that could be brought by such things. Also, there is a kind of control flow integrity because you call functions not by the address of the function, but by the index of the function. Then again, you cannot try to call something that was not designed to be a function. There is also no return address. So ROP, return-oriented programming, is not possible by design in WebAssembly, unless, as we'll see, there are differences. Applications are isolated, which is also something interesting, and the API is very simple. So at that point, looking at the security description, I was just looking at that and saying, okay, is WebAssembly the chosen one? Is it really the thing we expected for a long time now? And the answer is, it's going to be more complicated than that. The security is defined by three things. The module itself, where you could find programming errors, compilers, and so on. Malicious intent, of course, because if there is a malware, it will be loaded in module code. The VM isolation itself, and the feature allowed by the specifications. We're going to look at these three things quickly to see if security is really ensured. So about the specifications, currently, it's true, the specifications are very simple. However, this simplicity is causing problems because major actors are willing to include many more things into the WebAssembly specification, and there have been additional specification proposed for more things, and especially, for example, as I said, the WebAssembly is currently not able to access the HTML structure, what we call DOM of a web page, and that is annoying for web users and designers, for web developers. So people are trying to push for more specification, more features, and all of these features are absolutely not oriented for intended for security. They are intended for performance. So the current situation is satisfying for the specification, but it might not last as long as we want. Again, not going to go into the full details, but the compilation. Using a binary format also means that things are by design obfuscated. Analyzing a binary module is much more complex than analyzing an HTML page. And analyzing JavaScript is already very complex. Imagine having to do the same into binary compiled code. So this obfuscation is very complex for us. There is, as always, in compilation, a loss of information, which means you might not be able to get the semantic of the source program just by looking at the resulting binary. Also, the passing of arguments for function calls is quite complex. Since there are no pointers, the host machine is forced to allocate memory and give that back to the guest application. This leads to some black magic functions to be able to do this allocation. This is rather complex and error prone, and all of this result in a complexity that will result in danger for application. Also, and we'll see why this is especially important, since the execution environment is granting that there is no, for example, return address, the compiler will not install modern protection like stack canaries to ensure the stack is not overwritten, randomization, or things like that, because environment is supposed to make them unneeded. And as we'll see, optimization will make this a bit different than what was intended by the specification. And why is that? It's because of the just-in-time compilation. So WebAssembly is by design made to be very easy to compile into native code. So if you imagine that, for example, your browser is trying to execute the WebAssembly code directly, well, it's not true. The reality is that WebAssembly code is, again, compiled into binary code for your processor this time. So it's either ahead of time or just-in-time compilation, which is very simple and quite fast. And the VM properties make verification of these security properties. However, that leads to problems because this all relies on the verifications that are done before compiling the bytecode, the WebAssembly bytecode into native code. So if these verifications are incorrect or not sufficient, this will lead to introducing again security problems. And as we'll see, the most potential memory problems that can happen are type confusion vulnerabilities. And also, since protections were not introduced previously, this opens the door for stack heap overflows and so on that were normally not possible if using a virtual machine. So the just-in-time compilation will reintroduce dangers for the execution of the bytecode. And this has already happened in the past. If you look at these CVEs, I just took a few of them, but this is exactly parsing errors, type confusion, overflows, and so on. So this already happened. Here I'm looking at errors in the V8 engine, but the same happened in other implementations as well. Also, as I said, the specifications are currently quite simple. That is great. And the compiler is compiling, well, native code to WebAssembly. But sometimes the compiler is not your friend. The most common compiler for C and C++ to WebAssembly is MScript. So this compiler just takes your C or C++ source and outputs both a JavaScript module and a WebAssembly module, the JavaScript module being used to load the WebAssembly code. But the thing is, it also provides so-called useful functions like MScript run script, which is used to run any string you give it as JavaScript code. So what it does really is that it provides a way for WebAssembly to execute code outside its virtual machine. This code being able to access again the entire environment of the web page, and it can, for example, change the JavaScript function and the WebAssembly calls. Imagine using that for obfuscation. that makes common analysis tools completely useless, because to analyze such code, you would require to load both JavaScript and WebAssembly and analyze the interaction between both, and more obfuscation can happen. So this is very complex. And the overall security is granted by all of that. But the specification describes something that is ideal. It's not really something that is happening in the real implementation. So as you can see in the references, there are a lot of vulnerabilities that happen because of the implementation errors. So in my opinion, this should not exempt the compiler from adding the verification. And also, the consortium should be very careful in the feature it will try to add in the upcoming new releases. So I'm going to give you one example of wrong use of WebAssembly. So why is WebAssembly interesting for malwares? Well, malwares were previously using mostly JavaScript, maybe sometimes Flash, and WebAssembly is much more faster. That is the first thing. It's also portable, which is very interesting, and it's obfuscated. So these things are very, very interesting for malwares, and especially for crypto miners. We'll see one example of that. From a 2019 study presented in DIMVA, there were 900 sites in the Alexa top 1, and half of the WebAssembly modules found in these websites were malicious. And it was most likely code that was injected, but was so obfuscated that it was not found at that time. So this is just an example. We'll see one example right now from such malware using WebAssembly. So one day appeared something called Coinhive. Coinhive is a crypto miner which was not designed to be, well, at first, illegitimate. It was a miner designed to offer an alternative way of generating money for alternative to hosting ads. So the idea was you want to go on a website. This website will make your browser mine Monero, crypto money. And so it does not require to display ads. It will generate money just by making your browser mine Monero, sorry. It was designed to be very fast. It was said to be 65%. It comes from the Coinhive webpage. So it was advertised as 65% faster than a native, 65%, sorry, of a native miner. This made it very interesting for bad actors. And quickly, some actors used it to make illegitimate mining. So the idea was to insert such miner into a web page. So your browser just goes to some web page you were intended to, and if you're not looking at the CPU usage, you will not realize that your browser is mining money, and it quickly became #1 malware in the world. It was found in websites like, for example, the San Diego Zoo website. It was especially injected in WordPress and Drupal websites that were not up to date in terms of patches. How do you detect Coinhive? Going back to the IDS interesting stuff. Well, the name of the functions did mention the hash used and the mining used. So there were at least 3 functions with a name of kryptonite something, so kryptonite create, destroy, hash, and so on. And signatures were created based on those names. Well, we can be satisfied with that, but the fact is these signatures are very fragile because of course, the malware only has to change function names to escape detection. And that happened because Coinhive itself was discontinued in 2019, but other copycats followed, just changing things and improving the Coinhive miner design. So they used less obvious URIs, obfuscated codon strings, and changed function names. So the detection was not enough to completely detect the malware. And I think we need more stuff to be able to detect that. What other malware types could we find using WebAssembly? Well, it's already used for content obfuscation, so this is not new. But we could be scared of much more dangerous or more difficult to detect use case like VM escape, which is kind of tricky to detect, browser exploitation, and so on. So this leads us to the interesting part, which is what can we do to detect malicious WASM modules? Well, first of all, we need to extract the WebAssembly module. So how do you get it? Well, you get it into the transferred file in the underlying protocol. So this means we will have to cope with TLS 1.3, quick, HTTP 2.3, and so on to be able to extract files. This might cause problems because it might be not so easy to do. Also, disassembling the binary is very easy because the WebAssembly specification was designed to make that easy. But the code analysis has the same cost as reverse engineering, which usually takes one guy that you need to pay a lot, and you have to give it some time to be able to reverse the module. So if we want to be able to do that on the fly, that will be very, very complicated. Also, in reality, WASM binaries tend to be very big because compiler has to embed the language runtime, so the libc or the Python runtime, and so on. To be able to analyze that, we need static or dynamic analysis. And this is not something that is really easy to do, and especially in an IDS. Also, there are lots of FFI and cross-language calls like JavaScript to WASM and WASM to JavaScript. So if you combine that with obfuscation, with malicious intent, and so on, we might at that point wonder, is this really the job of the IDS? Is it something that we want to do in Suricata? I'm not sure of that. And I really think there is place for additional tools that needs to be connected to Suricata to do that kind of stuff. Detecting the module itself is fairly easy. You just look first at the extension, of course, which is supposed to be WASM, but it's not mandatory, and the file magic. So it's fairly easy to detect. But there is something that is a difficulty here. It's that not all WebAssembly files are malwares. So to be able to distinguish a malware from a benign WebAssembly file, we will need content inspection. So currently what we can use is just YARA rules, for example, or looking at function names, but anything other will require to be able to inspect the WASM module. And this requires then again new tools which are much more complex than just looking at the envelope of the WebAssembly module file. We can also use other key elements to detect WebAssembly malicious intent by, for example, looking at the JavaScript wrappers, because these wrappers has to instantiate the WebAssembly virtual machine and module for each of the module they would like to load. So we can have a look at these modules and then at the function calls to and from this module from the JavaScript code. Of course, we can also look at other things like WebSockets and the keywords in TLS connections, like, for example, the SNI that was used for some of the Coinhive signatures too. But the fact is, at that point, we need more tools. And the currently existing tools are either experimental or emerging, but they are not quite ready for the use in a streaming application. So I give here a few names of very interesting projects, but these tools require a complex integration if we want to manipulate them from Suricata or from an application. So what can we say in conclusion? Well, WebAssembly is here. We cannot avoid it. We will have to detect things related to WebAssembly. But the fact is, this is not so easy. WebAssembly is bringing things and difficulties that were previously related to binaries and applications on full-scale computers to the web. And that brings more and more difficulties because this is really easy to be used by malwares because of the obfuscation, because of many things. So here I would say new code because WebAssembly is recent, but old worries because everything we said is already known and used for many things since many years. But this is going to be here in the browsers for the next few years. And this is going to be very tricky for an IDS, for like Suricata, because this requires at least cooperation from the IDS, if not full analysis from the tool itself. So I will conclude in a kind of a troll question, but at that point, WebAssembly is bringing something which is really interesting, fast, performant, and very good for the web designer. But is it going to be the new Flash? Well, I'm going to look at that in the next few years. Thank you for your attention. I'm going to be present now to answer your question if you have it. Thank you.